Uh, okay, so I am Prakriti. I recently submitted my PhD thesis with Pratik. My original title was this, but since this is not an astrophysics conference, so I thought I would have more broad title. I will talk mostly about general ideas on the CGM and how astrophysicists study it. This is a little more technical and it's the main topic of my PhD thesis. I'll show some key results at a qualitative level. So here multi-phase really means multi-temperature, which we can observe at different wavelengths. And just for a quick reference, this is one of my simulations, and this is also one of my simulations, but these are at different scales. So this is like a few hundred kpc, and this is few tens of kpc. This is within 50 kpc. And we also have wonderful observations at different scales. This is in X-rays, this is in H alpha, so this is emission line, and this is a continuum X-ray radiation. So the clumpy structure here, this is more dense and cold gas, whereas this is hot volume feeling gas. And how hot or how cold, I'll come to that very soon. So with this, I will start my talk. First of all, I will try to tell what CGM is and where we find them. And how exactly we study them as a fluid. So this is how the universe looks at very large scales. And as you can see, there are several different kinds of structures. There are knots, there are filaments, and there are empty regions which are shown with black here. And these knots and filaments are where things are clumping. One small knot is zoomed in here, and this is what I showed in the first title slide. These are the kind of systems that we study, and these come in various masses. As you can see, some are bigger knots, some are smaller knots, and the mass of this also scales with the size of the objects. So if it's massive, it's usually also large in volume. So fundamentally, there are two kinds of fluids that we study in astrophysics. One is the dark matter, which forms all these backbone or the structures of the universe. And this is studied as a collisionless fluid, as Pratik also mentioned in his talk. These are studied with n-body simulations traditionally, and also smooth particle hydrodynamics. There is something which is more interesting, which is gas. Which is what we understand as the matter, and the special thing about this gas is that it is affected hugely by the gravity, underlying gravitational potential wells, which are formed due to the dark matter dynamics all over the place. And another important thing about gas is that it radiates and absorbs, it emits and absorbs photons, which we can directly observe. So gas is something that gives that kind of traces all of these, because this is something which we observe. And as I mentioned, that gas comes in different, gas appears to be at different temperatures, which we see at different wavelengths across the electromagnetic spectrum. So when I talk about multiple phases, and I mentioned that this gas radiates, first of all, what kind of radiation do I mean by all this? This is a global radiative cooling rate as a function of temperature. So all these small units or knots of gas, these appear at different masses and as a result different temperatures. So some are massive ones are very hot. This is 10 to the power 7, 8 Kelvin. This is somewhere here. Smaller objects are somewhere here. So accordingly, the gas also emits. So for example, in the massive mass scale, it's mostly Bremsstrahlung emission, which is what we see in X-rays. At smaller masses, it emits the atomic hydrogen or the first ionized helium. These are for zero metallicity. One confession to make, by metals we mean anything higher than helium. Oxygen is also a metal for astrophysicists. So this is for higher metallicity, like this the first line is where there is no metal, and these are the successive lines with higher metallicity, which we denote as Z. So lambda, which is the cooling function, this is some kind of an equilibrium function, collisional equilibrium, photoionization equilibrium. So this lambda is very important, and we, for a larger scale simulation, we always use this global cooling rate. And accordingly, we calculate the cooling timescales. So I will now tell more about the hot gas and the cold gas that I start with. So for massive gaseous halos, as I said, the temperature is very high, and the masses are also as high as greater than 10 to the power 4 solar mass. This is dark matter plus gas. For smaller systems, this temperature, the gas temperature, so for smaller system, the gas temperatures are slightly smaller, and this is that emission line, hydrogen and helium line that I showed in the cooling function. So what sets this kind of temperatures in these halos or gaseous systems? That's basically the dark matter evolution causes a gravitational potential well to be there at the location of each knot. And depending on how massive the knot is, that is how much dark matter is there, this potential well could be deeper and deeper. And this just forms the gravitational well for the gas, which falls into this. And at the bottom of this gravitational well, it is roughly in hydrostatic balance. Now, it's actually not so smooth, of course. This is some kind of a time average representation. This is basically a cartoon of the potential well. So the gas that is outside, which is still falling, it's usually supersonic. The velocity is again set by how deep this potential well is. And as soon as it comes across this hydrostatic gas, all the kinetic energy is thermalized. So this gas is shock heated, and that's how it gains such high temperatures. Depending on how much mass is there inside this hydrostatic medium, this temperature could be higher. So as you can imagine, across redshift or across time, the temperature will gradually be higher towards the outskirts. Okay, so usually at the center of the halo, there is a galaxy which is much colder in terms of temperature than these volume feeling hot gas. So this hot gas, which is all over the volume of each unit, is usually very hot, and it's kind of maintained at that temperature. So it remains hot. As we see in the observations, the general expectation is that the cooling time scale, I showed how we calculate cooling time scales. So for very massive systems at very large radii, this cooling time scale is comparable to the age of the universe, but not inside. So the expectation is that all these things must cool and just fall, just lose pressure support and just fall. But it usually doesn't happen. So there is no evidence of monolithic cooling. By monolithic cooling I mean that entire region just cools isotropically and homogeneously. So the reason is that there is So the reason being that there is a continuous injection of energy into the medium that maintains this medium almost hot all the time. In a time average sense, again, not locally. So one source is black hole driven feedback. This is the radio emission shown. Also, Pratik showed some of the images. These are like 100 kpc scale cavities which emit brightly in the radio. The background blue is X-ray, that is the hot gas here, and there is cavity here, means there is no gas, and this is just emitting radio synchrotron. This is the image of a molecular cloud, which is like stellar, which shows stellar outflows as well, which is locally keeping this region hot. So basically, on a time average sense, we can imagine that this this entire bulk of gas remains hot more often than not. So, there is always, so one question is that if there is stellar winds, stellar outflows here, that means there is some star formation, then everything is heated up, then this bulk is also heated up, then how is the galaxy getting its source of cold gas, or how is star formation fuel replenished into this medium? So there must be some cold gas source. And when this cold gas is less than 10 to the power 4 Kelvin, that's what we call condensed gas, which is very cold. It usually is always forming stars. So one scenario is that the gas that is falling into this potential well gets shock heated, but there is also some gas which is very dense and it doesn't go through that shock heating and it directly falls into the central galaxy. So this can keep fueling the central galaxy. This is one of my simulations. It shows that large-scale filaments, if you remember the large-scale universe picture, there are knots and there are filaments. So I initialize with a small, tiny gaseous unit here and dense filaments here, and this keeps fueling the central region. But the survival and coherence of these systems are questionable, and it's open to research because of Kelvin-Helmholtz instability, which can cause, because this gas is very hot. This region, this filament is surrounded by hot gas once it enters the shocked gas region. So this may not survive actually. But in principle, if it survives, it can keep on feeding the central galaxy with colder components. So another scenario that also Pratik talked about is within the shocked diffuse region, if there are smaller, tiny local regions which have density fluctuations and which just grows. So this is like cold gas coming out of the diffuse phase, forming out of the diffuse phase. And there is elaborate theory on this, linear theory on this by Field in 1965. This can kind of explain some of the H-alpha emission in tiny regions, localized regions around the galaxies. So basically, the linear theory is very, very well known. If there is we can imagine a growth rate to be omega, and it grows as 1 by Ti, where Ti means thermal instability. This is a thermal instability timescale, which is related to the cooling timescale. Remember that this lambda is what I first showed as the cooling function. So this and these are same. So basically in simulations, what we try to do is that we keep on pumping energy at each time step and keep each radial shell in thermal balance. So basically if this is the cooling rate, then we inject equal amount of heating in each shell. So this is how the fluctuations, density fluctuation with different amplitudes look like. This is a gaseous halo with higher fluctuations. This is with lower fluctuations. One of the things that we try to do is that putting constraints to cooling time to freefall time. This is a typical radial profile. And in simulations as well as observations, people are really interested at this minimum value of the cooling time to freefall time and the level of density fluctuations that we can see. So basically, cooling time is, I have shown this again. I'm showing this again. So cooling time is just calculated as energy times the cooling rate, and freefall time is just the freefall time in presence of only gravity. And previous simulations have talked about threshold value of this. So a lot of my work was putting constraints to this ratio. Each of these points are each simulations, and we try to scan out parametric space where all these class of circumgalactic medium will show condensation in tiny localized regions, while all these will not show. So this is one of the interesting things that we did. So I have. You're out of time. Okay. Okay. So I will quickly tell about CGM, ICM, what the summary is about. So it's a complex astrophysical gas, and it can be studied, it can be magnetized as well. So I did primarily hydrodynamics. The difference between other terrestrial gas and this is that it's strongly affected by gravity. There is a huge variation of density and velocity because of gravity. It radiates and absorbs, that is, we can actually see it. So this makes it really interesting. So gas also comes in multiple temperature ranges, and there are several scenarios how we can explain how this cold phase comes up, because the underlying gas should be hot. So I primarily worked on this. There are other scenarios. This is what I'm working on right now, and this is not something I mentioned before. So in local thermal instability, I talked about this part, but there are several different thermodynamic properties that we can actually see the effect on local thermal instability. One is entropy, one is metallicity. This is something I'm working on with one of the undergrads here. And yeah, so I'll stop.
Yeah, fortunately.